Welcome to Forces and the Laws of Motion, Chapter 4. This is part 2 of a video series. I believe there is only one more, possibly two more parts, depending on how I break up some of the skill and math applications for forces. There may be an additional video there. In any case, though, this is part 2, so this is a continuation of the first part of Chapter 4, which I believe covered sections 1 and 2, and this will pick it up at section 3. As always, I encourage you to read the textbook and make sure that you're familiar with the concepts before I go into this particular presentation. Simply because this presentation is a summary of that information and does not provide all the context that you may need to understand how the concepts relate to each other and how they can be expanded out to the greater view. Okay, here are the objectives for this section. I do not see any asterisks beside any of these objectives, so they probably come straight out of the book, maybe paraphrased to some small degree. Wanting to look specifically at acceleration, mass, and how they're related to net force. Being able to predict both direction and magnitude of acceleration with net force, or vice versa. And look at action-reaction pairs as related to Newton's third law. Okay, Newton's second law of motion, recalling that the first law reads something like for every, actually I was about to give the third law. An object in motion will stay in motion, an object at rest will stay at rest unless acted upon by some unbalancing force. That would be a paraphrase of the first law. Newton's second law is about acceleration and how acceleration is directly proportional to net force and inversely proportional to the object's mass. So mathematically, if you take this statement of Newton's second law, which is really more of an observation of motion as opposed to a law of motion, if you get into exactly what a law is, but they've been called laws forever, so we'll just stick with that. Mathematically, then, acceleration is equal directly proportional to the net force and inversely proportional to the mass. So if you show mathematically what it looks like, this is exactly how you'd write it, but how you actually see it is down here, F equals ma. It's very, very classic, if you will, where F is really the net force and then mass times acceleration over here. And the net force is, of course, the summation of all forces acting on an object. And if the net force is anything other than zero, then there will be some sort of acceleration. What this implies, and it implies quite a deal, and this is by no means a complete list, and I'll investigate this possibly in a flow chart if I can figure out a way to come up with a clear flow chart. But otherwise, we'll explore this further. But what does this imply, this F equals ma? Well, of course, the net force is equal to the mass times the net acceleration, because remember, acceleration has direction, and there can be net acceleration. What does this also mean? Well, the net force is equal to the summation of forces, and the summation of forces can then be expanded out to any applied forces plus any resistant forces, realizing that one of these will be a negative value. So actually it is a summation. That probably should be a plus sign. And one of these would be negative, taking away from the other, because they would be, at least it's implied that they're in opposite directions. But what else can it imply? Well, the net forces can be something to the effect of an applied force less the force of gravity, or plus the force of gravity in the downwards direction. Remember that the force of gravity can then be expanded to mass times gravity. That's the pull of gravity down on a mass using the gravitational field strength constant of 9.81 newtons per kilogram. So that can also be a summation of forces. It really depends on, are we talking more horizontal or are we talking more vertical? Net forces can equal then applied force less mass gravity. That's simply taking this and expanding it downwards. So these two are exactly the same. Very simply put, it can be the force up versus the force down, summation of those, but one of them would be negative. So you can show a minus sign, if you will, or you can add the negative. That's certainly up to you. The net forces can be potentially an applied force combined with friction, friction being in the opposite direction. One of these two values would be negative, so the summation would be smaller than either one of these two values. So what we can then do is we can take MA net, because this is all F net, force net. The net forces are equal to all of this. Therefore, all of these that we are talking about over here are equal to the mass times the net acceleration. And so everywhere you see F net, I could replace it with MA net. So mass times the net acceleration is equal to the summation of forces, which can equal any applied force less or combined with any negative resistance force. Now the applied can be in a negative direction and the resistance can be in a positive direction. Negative and positive, that's just direction. That's all it is. If any forces are not parallel or perpendicular to each other, we will need to employ trigonometry functions in order to isolate component forces, make them parallel, so we can then add them together. Because you can only add parallel forces, like back and forth, to left and right, side to side, those types of things, up and down. Okay, problem set C in your textbook covers Newton's second law, and there's really a lot to Newton's second law. Even though F equals ma or F net equals ma net seems very simple, there's so much implied in all of that. But let's take a look at this example here. A 2.2 kilogram book slid across the table, experiencing a net force of 1.6 newtons to the right. So what is the book's acceleration? Well, I went ahead and worked this out. So this is the whole thing right here. Here's a diagram. I have this book, 2.2 kilograms, a net force, pushed it to slide it across, and I just created some notation along with my simplified force diagram. I did not do agent notation. I just went real simple in this. So normal force, applied force, force of gravity, force of friction, kinetic friction is technically what it is because the book is moving. As opposed to table on book, applied force on book, earth on book, and table on book again. And you could do a system schema here. So normal force, gravitational force, remembering that Fg, gravitational force, is equal to mass times gravity. So we can determine what that force is. The applied force, kinetic friction. Okay, so in the up-down direction, there is no movement. So what I do know is that the normal force must equal the gravitational force, of course, in the opposite direction. I know the force of gravity is equal to mass times gravity, and I know the mass of the book. So 2.2 kilograms multiplied by negative 9.81 newtons per kilogram gives me then a normal force of 22 newtons, and the force of gravity in the downwards direction is also then known as a negative 22 newtons. So movement to the right is due to a net force greater than 0. The net force is equal to the sum of all forces acting to the right and left in this example. And also the net force is equal to the mass of the object multiplied by its acceleration. So these are the things that I know about this book and the fact that it is moving, it is accelerating. And so let's investigate that in the next slide. Okay, so I just recopied that, the summation statements there, and let's see what that then implies. Okay, so number one, the net force is the sum of. So here we go, number one. So the net force is equal to the sum of the applied forces plus friction. Remember, one will be in the negative direction, and I know that all of this equals 1.6 newtons. So while we do not need to determine the applied or the kinetic friction, it's good to know that the relationship exists, how it exists, and the fact that they will sum up to 1.6 regardless of what they are. Number two, also, the net force is equal to the mass of the object multiplied by its acceleration. So let's take a look at number two. So F net equals ma net. I didn't write the net down. Rearranging to solve for acceleration, I have the net force divided by the mass equaling the acceleration, and I have numbers to plug in there, so it becomes a plug and chug. Net force 1.6 newtons to the right divided by the mass 2.2 kilograms of the book equals this value here. And the acceleration units, meters per second squared, indicating it's to the right, it's positive. So there's my answer. Now just a note on units of measure. Let's go down here. A note on units. A newton. A newton is a derived unit named in honor of Sir Isaac Newton. But it's a derived unit which is the product literally of mass times acceleration. So the newton itself is a kilogram multiplied by a meter per second squared. thus giving us the kilogram meter over second squared. So 1 Newton equals 1 kilogram accelerated at 1 meter per second squared. So therefore, when I plug it in up here, the kilograms actually canceled denominator here to numerator, leaving meters per second squared. So that's how those units worked. Okay, moving on. So Newton's third law of motion, a lot of people know this law, whether they understand its implications or not. For every action, there's an equal and opposite reaction, indicating that forces act in pairs. If I push on the wall technically pushes back. How strong does the wall push back? Well, how strongly am I pushing the wall? Everyday forces. Okay, so this is actually section 4. I thought there was more to section 3 there, so. But section 4. So section 4 is on everyday forces, and these are the objectives out of the textbook on the last section of the chapter. Explain the difference between mass and weight. Very critical there to a scientist that they are very different from each other. Find the direction and magnitude of the normal force, which we have done some work with the normal force before, which is the support force. Describing air resistance as a form of friction, and then there is some mathematics with friction that we can get into. Now that will not be in this particular presentation, that'll be further, but with this presentation I wanted to at least discuss through the normal force and introduce friction. Okay, weight. We talked about weight, and weight, matter of fact, was the first model that you discovered in the Unit 4 paradigm, where the force of gravity is the mass times gravity, and the gravity being the G, being the gravitational field strength constant. This is a scalar form of gravity, so for weight itself, you just ignore positive and negative signs. So, what is my weight? I weigh 65 kilograms, and then I convert that over to newtons, and it's roughly just under 650 newtons. But there's no direction associated with weight. As opposed to force of gravity pulling me down, now I'm talking about direction. Okay, we already know what the normal force is, so you can take a look at this yourself. There is an example, TV on a table, gravity pulling down, TV's not moving, therefore something must be holding the television up. We know that it's called the normal force, sometimes called the support force. So a diagram would look like this. So here's the TV on the table. And here would be the normal force in the up direction, supporting from the table, gravity on the earth, gravity of the earth pulling down, and of course if I did agent notation, table on television, earth on television as well. Moving on. Friction. Friction, of course, is a resistant force to motion, and it's a result of objects coming in contact with each other, so it's a contact force. With that, there are two ways that we can look at friction generally. One is static friction. And static friction is simply a restive force that comes from surfaces in contact that keeps the object from moving. As long as the object is not moving, we know that the static force friction is going to be equaling the applied force. So those two are going to be equal as long as the object's not moving. So that's you pushing on something on the desk, and it actually doesn't move. So you push a little harder, it doesn't move. You push it a little harder, it doesn't move. And you'll go all the way up to the maximum static friction that object can produce with the surface it's in contact with. And then once it starts moving, you have overcome that level of static friction. And you've broken the electrostatic bonds that exist between the surfaces. Then you go to kinetic friction. This is when the applied force is greater than the maximum static friction force. The frictional force that is at work on an object that is in motion and is in contact with an object is called kinetic friction. And this, the net force acting on an object is the difference between the applied force and the kinetic friction forces at work. So in one case where we revisit the net force, any applied forces plus any frictional forces, remembering one of these will be in the opposite direction of the other. So most of the time you see plus signs here, and then just assuming one of these values is negative. So therefore the net force will always be smaller than either of these forces. And the applied force will always be magnitude-wise greater than the frictional force. Otherwise, the objects would not be moving, or, well, actually, friction would not move it backwards. So it would stop it, but it wouldn't move it backwards. So the applied will always be greater, but the difference in the two will give you the net force. Okay, I believe this is the end of the presentation here. We'll investigate friction in greater detail, as well as the implications of net force and various conditions of how we can look at net force. Interestingly, with net force, like Newton's second law, net force equals mass times net acceleration, F equals ma. That acceleration being brought into the equation about the actual motion will link our now causal models, the cause of motion change, which are forces, with our motion units, where it was just about the motion itself without cause. And so the acceleration is the bridge there to allow Unit 3 models and Unit 4 and 5 models, which are the force models, to actually kind of coexist and work together to allow us to investigate time of travel, if something is going to stop, if something is going to speed up to a particular speed, that we can use F equals ma and the acceleration a bridging over to our velocity, acceleration, and time models for Unit 3 with objects experiencing uniform acceleration, whether they're speeding up or slowing down or changing direction. So that'll be in a future video. Thank you. Let's see, diagramming. I'd forgotten I had included this. So with a diagram, of course, just realizing that friction is always parallel to the surfaces in contact. So here I have the infamous box on a ramp, or an inclined plane, and normal force is always perpendicular to the surfaces in contact. Friction is always in the opposite direction of the motion, assuming the motion is or will be down the ramp. Force of gravity is always perpendicular to the surface of the Earth, and therefore, because we have forces that are not parallel and perpendicular to each other completely, we would then employ trigonometry to take a look at what gravity is doing as far as parallel and perpendicular to the other forces. Thank you.